Reflections. When I recently saw reflections of a mirrored cylinder, I asked myself, what and in which way information from the environment is projected on its surface. Everybody understands the information reflected from simple planar surfaces, but for evenly round surfaces like cylinders, the situation becomes interesting. If we project a ray hitting our cylinder in the direction of the cylinder's center axis, we see that part of the problem can be understood from examining intersections between circles and straight lines. So, let's solve the simple geometric problem and provide a compact vector form description of the intersection points P1 and P2. We start with the origin of a standard two-dimensional coordinate system. In the next step, we have to define unambiguously the configuration of our geometric objects. So, let the origin of our circle fixed by vector O. The radius of the circle is r. Next, we point to the origin of the straight line using a vector v and fix the direction of the line by another vector d. Here, the check above the letter d indicates that the length of this vector is, without loss of generality, 1. With other words, d is a unit vector. After all geometric objects have been defined, we are ready to calculate the position of the intersection points. Therefore, we need two basic equations for our geometric objects. First, we denote a parametric form of the circle. Every vector pointing from the circle center to the circumference is of length r. Here we use the squared length because this term can be conveniently expressed with a scalar product, which we will use in a second. As a further input for our calculation, we parameterize the set of vectors pointing to our straight line. With a parameter t and a unit vector d, we can assign a vector to every point on the straight line. To find the intersection points, we now ask, for which parameter t is also the circle equation fulfilled? This question can be answered by inserting x of t into the circle equation and then solve for t. First, we use the scalar product to substitute the squared norm. Because we want to calculate t, we are interested to sort terms in this equation according to the powers of t. Here we realize that the norm of d is 1, which helps to further simplify our equation. Shifting all terms to the left side, we end up with a reduced quadratic equation for which the solution is well known. Inserting t into the equation for the straight line will finally provide the position of the intersection points. And that's basically it. Just one final note. We started with simple equations for a circle and a straight line and ended up with a rather complex term for t. Luckily, it's possible to interpret our solution and assign a geometric meaning to the form, which I will probably discuss in another video.